We're going to wrap up chapter 2 today, talking about inverse functions. And as part of today, we're going to do some review of things that we have done in our guided notes before. First, let's start with definition of a relation. Remember, a relation and a function are very connected. A relation is any set of ordered pairs So if you want to think about a graph of a relation, you could draw whatever you wanted on that graph. It doesn't have to follow any rules. Any set of ordered pairs qualifies as a relation. A function, we start to make some rules. We start to narrow our definition. A function is a relation in which each independent variable, remember those independent variables are our x values or our domain, corresponds, is paired up with only one dependent variable. Our dependent variables are our y values. They make up our range. I know I've got a function if it passes the vertical line test. So if I'm looking at the ordered pairs, I'm looking to make sure each x is paired with only one y. If I'm looking at the graph, I want to make sure that my function passes the vertical line test. So let's do f of x equals x squared. We got to be super comfortable with our quadratic function at this point. 1 squared is 1, 2 squared is 4, 1, 2, 3, 4, 1 and 4. So there's our quadratic function, our parent, our parabola. I see that the x value 2 is paired only to the y value 4. The x value negative 2 is also paired with 4, so those y values get to repeat. That's fine, that's not a problem. But our x values are individual. Each x has only one y. This passes our vertical line test. It's a function. Now we're going to narrow our definition down once more to a one-to-one function. A one-to-one function is a function in which each value in the domain, again these are our x values, corresponds to, and here's our difference, a unique value in the range. So for a general function, each x has one y, the y values get to repeat. For a one-to-one function though, each x has a unique y. The y values do not get to repeat. The one-to-one functions are going to pass that vertical line test. They are a function, but they also pass the horizontal line test. So knowing that, my quadratic is a function because it passes the vertical line test. It is not one-to-one because it fails the horizontal line test. Another interesting thing about one-to-one functions is that they are invertible in the sense that their inverse is also going to be a function. If I invert my parabola, the inverse will not be a function. I can invert it, but it doesn't give me a function. If I invert a one-to-one function, the inverse is still going to be a function. So let's think about our parent functions that are one-to-one. So I've got 4 of our parent functions here. Let's sketch those parent functions. Quadratic looks like this. Square root looks like this. Absolute value is my v, and my cubic function. Now these are all functions. They all pass the vertical line test. To check to see if they are one-to-one, I want to see if they pass the horizontal line test. Well, we already said quadratic, that's not a horizontal line. That was awful. I'm sorry guys, I got in a hurry. I was talking. Let's do that, make it a little neater. This quadratic is not one-to-one. So I can invert it, but the inverse will not be a function. What about my square root? Passes the horizontal line test. It is one-to-one. So if I invert the square root function, its inverse will be a function. What about our absolute value? Fails the horizontal line test? Not one-to-one. Cubic function? I can draw any horizontal line I want. It only crosses one time, so it is a one-to-one function. So you see the difference. One-to-one functions, each x has a unique y value. Y values are not repeated. All right, specific qualities of a function and its inverse. To find an inverse, function and its inverse, the domain and the range switch places. The domain becomes the range becomes the domain. So if the point 0.25 exists in the function, then the point 0.52 exists in the inverse. That's my inverse function notation, and you can see that my x and y values switch places. Second, a function and its inverse reflect across the line y equals x. Y equals x is my parent linear function. So if I have a function and its inverse, they are going to reflect across the line y equals x. That's my line y equals x. So let's think about what that might look like. Do something really simple. If I have a function that looks like this, let's see, there, that's my function, and it reflects across the line y equals x, it's going to reflect right there, reflects across that line y equals x. Okay? And then number 3, the composition, remember composite functions? The composition of a function and its inverse is always equal to x, no matter which order I do it in. F composite F inverse of x is equal to x, and F inverse of f is equal to x. So whichever order I do it in, if I do a composition of a function and its inverse, the answer, the result, is going to be x. Okay, let's look at the next page. All right. Quality. I'm sorry. I lost track of what I was doing. Here are 3 qualities. Let's talk about them in more detail. Number 1, we say that our domain and our range of the function and its inverse switch places. So, given the following function, we're going to create its inverse by switching the domain and range, and then we're going to evaluate to see if the inverse is a function. So is this a function? Well, my domain value is 1, 2, 3, 4, 5. So yeah, this is going to be a function. F inverse means that for each of these ordered pairs, the x and the y switches places. Is the function also is the inverse also a function? Well, the answer comes out to be yes, because my domain here, 3, 5, 4, 9, 5, each of those x values is different. And the way I could have checked that is to look at my original function and notice that it is one-to-one. Each y value is unique. No y values are repeated. So I know that my original function is one-to-one, which means my inverse is also a function. That's that first quality, domain and range switch places. The second quality tells us that a function and its inverse will reflect across the line y equals x, that parent linear function. That's the line of reflection for a function and its inverse, and you can see I've got that sketched in here for both of these. Here's my function, passes the vertical and the horizontal line test, so it is one-to-one. I need to reflect it. Now, I'm not very good at reflecting things across lines just by visualizing it, so I'm going to use this first quality to help me do this reflection. This point is at 1, 5, which means it has a corresponding reflected point at 5, 1. This point is at 1, 2, negative 3, 4, 3, which means it has a corresponding reflected point at 3, -3. This point is at -2, 0. So I have a corresponding reflected point at 0, -2. There is the inverse function. So if this is f of x, this is f inverse of x. All right, you do the second one. I'm not going to talk you through it. I'm going to do it. You know what? I'm going to add an arrow there. If I add an arrow, you know what that is? That is a square root function. We've got a point here and a point there. Let's invert that. This point 0, 0 is on my line of reflection, so it's not going to move. The point 4, 2 becomes 2, 4. It is not on the line of reflection, so it does move. So there is that inverse function. I knew it was going to be a function because the original function was 1 to 1. All right, so first quality, domain and range switch places. That helps us with our reflections across the line y equals x. And then our third quality was that the composition of a function and its inverse is always going to come out to equal x. All right, we're going to practice that. We've got two functions, f of x and g of x, and we want to show if they are inverses of each other or not. So to do that, we want to do the composition in both directions. Now remember that order matters with composition of functions, so I'm going to start by taking g of x and plugging it in to f. So I've got f, I'm going to plug in the g of x function, so I start here, 3 over, and then I take out that x and replace it with the other function. So that other function is 3 over x plus 4. All right, let's start with the simple things. My denominator here, 3 over x plus 4 minus 4. Well, 4 minus 4, that's 0. Those are additive inverses. So now I've got 3 over x. This is a rational expression that's pretty complex. It's basically division, though. I have this big denominator. I've got this big fraction bar. I've got a numerator and a denominator here. When I'm dividing with fractions, I multiply by the reciprocal of the second term of the denominator. So my numerator is 3, just 3 over 1. If I multiply by the reciprocal of the denominator, that means I'm going to flip this upside down and it becomes x over 3. Division with fractions means I multiply by the reciprocal of the denominator. When I multiply, anything over itself is just 1, and I'm left with x. So we're looking good. It's looking like these two are inverses. But before we can say for sure, we need to do the other direction. We need to plug f of x into g to check. So g of f of x, my g function is here. So I'm going to start with 3 over x plus 4. That's my g of x function. And in place of that x, I plug in 3 over x minus 4. Now this one looks a little bit more complex, but you know what? We've got another complex rational expression here, big division problem. So we're going to treat it just like we did this one, and we are going to multiply by the reciprocal. So that numerator is 3. That's the same thing as 3 over 1. I multiply by the reciprocal of that denominator, so that x minus 4 goes to the top. Anything over itself is just 1. So that 3 over 3 is just 1. 3 divided by 3 is 1. So now I have x minus 4 plus 4. That adds to 0, which leaves me with x. So the composition of the two yielded x no matter what order I did. So the answer is yes, they are inverses. So again, I can invert anything, but whether or not an inverse is still going to be a function depends on if I start with a one-to-one function. Apparently, these are both one-to-one functions because when I do the composition, I discover that they're both inverses. All right, we've got one more example. I would really like you guys to pause the video, do what you can with this, and then come back after you've worked through it as much as you can and see how I did. That would be 4 over 1, so that cancels and leaves me with x plus 7 minus 7, which is x. And then we're going to go the other way. X plus 7 over 4, and I plug this in. Well, 4x minus 7 plus 7 is 4x over 4. Anything over itself is 1. So yes, they are inverses. Okay, excellent. I hope you did that on your own. And then watch to see if mine came out the same as yours. All right, how do I find an inverse function? We've talked about checking to see if a function is an inverse. Now we're going to figure out how to find a function's inverse. Well, finding the inverse of a function, we use the switch and solve method. Super simple, 4 quick steps. I promise, it's not a big deal. We've got an example function that we're going to work with right here. F of x equals 4x minus 1. What type of function is that? If I were to graph this, what is my graph? I want you to get in the habit of thinking about that. 4x minus 1 is a linear function. If I graph it, it's going to be the graph of a line. In fact, it's a line with a slope of 4. Y-intercept is -1. Super steep slope, so it's going to look something like that. Up here, also linear. Do you remember? You know what? That's not a variable in the denominator. That's just a 4 in the denominator, so I could write that as 1/4 times x plus 7, which is still a linear function. It's just x. It's not x squared, x cubed, square root. Well, those are both linear functions as well. Okay, so we've got a linear function. We're going to invert this. Linear functions are 1-to-1, so we know that the inverse is also going to be a function. My first step always is to replace our function notation with y. These two things mean the same thing. So I'm going to rewrite my function. Instead of f of x, I'm going to rewrite it as y equals. First step. Switch. Here's the important thing. Switch the x and the y to opposite places. Why would we do that? Well, remember our 3 qualities. Domain and range switch places between a function and its inverse. So I take this and I say, okay, I'm going to rewrite it as x equals 4y minus 1. I switched my x and my y. Next is the solve part. I'm going to solve for y. Well, I had it solved for y to start with. I switched the domain and range. Now I'm going to solve for y again. That's my new range. So I need to move everything away from my 4y. Let's start by adding 1 to move it over. So x plus 1 equals 4y. And then 4 times y, the opposite operation is to divide both sides by 4. Anything over itself is 1, so I have y equals x plus 1 over 4. Now my last step is to put the notation back. So I'm going to replace y with my inverse notation. Don't forget this last step. We had to do it in the first step. We had to take it out of our function notation. Now we have to put it into our inverse function notation. So y becomes f inverse, and that is equal to x plus 1 over 4, which is absolutely fine. I could also choose to write that. It is the same thing to say 1/4 times x plus 1, or to say x over 4 plus 1/4. Either way, these are equivalent ways to write that. This one could be 1/4 x plus 1/4, so that we have our slope-intercept form of our linear function, which we have not addressed yet, but we're going to get to really soon. All right, let's do a little bit of practice with finding a function's inverse. each given function is 1 to 1. You're being told. So its inverse is also a function. Now, but remember, we can't invert anything. It's just that if we invert it and it doesn't start out 1 to 1, the inverse won't necessarily be a function. We're going to use our switch and solve method to find those inverse functions. There are our 4 steps for switch and solve. Okay. Our first one, g of x, f of x, doesn't matter. We're going to replace our function notation with y. So y equals 3 over x plus 1. Our second step is to switch the x and the y. And then our third step is going to be to solve. Let me kind of define our space a little bit so that I know we won't run out of room. Our third step is going to be to solve for y. So I'm going to start out by subtracting 1 from both sides. I threw myself for a loop, but we're fine. X minus 1 equals 3 over y. Now, here is what I kind of got hung up on. I need to solve for y. I got to get y out of the denominator. The way I'm going to do that is to multiply by that denominator, to multiply both sides by y. When I multiply both sides by y, it cancels out over here. Anything over itself is just 1, right? So that is equal to 3. Now, I'm not going to distribute because I don't want to spread that y out. I want to solve for y. I want to get it by itself. This is y times x minus 1. The inverse operation is to divide. So that now anything over itself is 1. Y equals 3 over x minus 1. And my fourth step, my last step, is to put that into inverse notation. Now my original function was g of x, so my inverse notation is going to be g inverse of x. And I want to note that my variable's in the denominator, which means this is a rational function. Just like my original was a rational function. Okay. I want you to give it a shot with 2 and 3. Pause the video, see what you can do with 2 and 3. I'm going to work through them following my steps for switch and solve method, but I would like you to try it on your own. So pause the video, then come back after you've given it a good old try and see if I did the same things you did. So there is my change of notation. Here is my switch. And now my next step is going to be my solve. So x equals, you know what, I'm going to move that 1 over. Let me go ahead and move that. I'll subtract it over y cubed. I've got to finish solving for y. I need to uncube it. To uncube something, we take the cube root. Cube root of cube cancels out and leaves me with y equals. Can't simplify that. I would if I could, but I can't. Cube root of x minus 1. So this is a radical function. It's a cube root function, which is one of our parent functions. My last step is to replace y with my inverse notation. It started as f of x, so my cube root function is f inverse of x. So my original function is a cubed function. This one is a cube root function. Over here I started with a rational function. I ended with a rational function. What type of function is this? Variable in the denominator. It is also rational, so I kind of expect I will end with a rational function as well. First step, y equals. Second step, do my switch. Third step is the solve part. Remember how we got that y out of the denominator up here? We multiplied both sides by that denominator. That's the same thing we're going to do here. We're going to multiply both sides by that denominator. Not going to distribute. Cancels and leaves me with 7. Now over here on the left, I am multiplying. Inverse operation is going to be to divide that by x. Then I need to add 3 to move it over. And my final step is to put it into inverse notation. My function was h, so I've got h inverse of x. Started as a rational function, ended up still as a rational function, variable in the denominator. Now, one thing I want to encourage you to be sure you do, don't eyeball it and think you know what it's going to be, because you will end up with bits and pieces in the wrong spot. You will lose points, you will miss problems when you just could have taken a couple of minutes to work it out and get everything where it should be. For example, right here, if I eyeball that, I might do cube root x with a minus 1 on the outside, or I might leave it plus 1. That's wrong. Don't just look at it. Go ahead and work through the steps.